Okay, so this is, I guess, a follow-up talk to Pablo's nice talk yesterday. I'll talk about phase transitions and symmetry breaking in the current distribution of diffusive systems, specifically in the large deviation function. And I'll have to explain why these transitions are different than the ones that were discussed yesterday, and hopefully I'll do that. This is the work done with a postdoc, Youngju Boek, who's just finishing at the Technion and moving on to Cambridge, and our chairman, which will hopefully give me 90 minutes of talk time. Okay, so the setting is the sort of standard setting of diffusive systems. We have some a narrow channel. In this talk, I'll consider one-dimensional channel, which is containing some diffusive and interacting gas. So you want to think of some disordered phase of a system, which is connecting two reservoirs, which can be at either equal densities or different densities. And the size of the channel is set by L, its length, if you want. So the standard setting, and I'm interested in the probability of observing a current inside the system. And we know that the probability of observing a current in this class of system is described by a large deviation principle. So it decays exponentially with a large deviation function of the current times the time at over which we measure the current. So we're measuring the current over some length of time t. And L, I remind you, is the system size. And this is a standard thing that's been discussed almost in all the talks I saw here over the last 2 days. And the question that I'll be interested in, can this large deviation function be singular as a function of j? So namely, as I change j, is there some phase transition in this large deviation function? And I'll try to identify the class of models which can lead to phase transitions under the boundary condition diffusive systems. So just to relate to yesterday's talk and some other works, so these kinds of phase transitions before our work were very well known on rings. So for example, in Pablo's talk yesterday, he was discussing singularities in the large deviation function, and these were related directly to the fact that the system was sitting on a ring, and I'll discuss it later, but just briefly, the transition was from a stationary profile. If that doesn't make sense, I'll explain it later, to a traveling profile. And in our case, this is distinct because we have these boundaries which don't allow solutions of this. At least we're not aware that you can have these solutions in our system. So these transitions have been known to occur for the WASP in one dimension, going back to Bernard, Derrida, and Thierry Bourdieu, and WASP in 2 dimension, as was discussed yesterday, and the KMP in 1 dimension. And for boundary diffusive systems, if you look at one of the first papers on these current large deviations, at the end of the paper by the Rome group, they suggest that you could have transitions of the form that we discussed, but it's done in a very heuristic way. They say, oh, if these functions behave in this way, then you might have this transition. There was no microscopic model shown to exhibit these transitions. And actually, for a reason that I won't get into, if you want to know, come and talk with me after the talk. The actual scenario that they discuss in the paper is actually not the one that happens. The outcome is the same, but the actual scenario is different. Okay, so to answer the question that I'm giving you all the answers. You can have 2 types of phase transition in these systems. The first type is a symmetry breaking, a continuous transition in the large deviation function. You can also have first-order phase transitions in the large deviation function in these systems. And again, the mechanism is different from the periodic boundary condition problem in the sense that you're not going into moving solutions. From a technical point of view, and again, if you don't know the words, then I'll explain them later. We're not breaking, our transitions don't violate the additivity principle. The additivity principle holds everywhere throughout. And I'll give a general condition for which models and when they exhibit phase transitions. So in that sense, our theory is general. We're not starting from a microscopic model. From the fluctuating hydrodynamic theory, we give conditions for which models exhibit the transition. And once we find the conditions, we identify microscopic models which correspond to the transition in each scenario. And what I want, Pablo was sort of indifferent about it, but I sort of find it interesting that these transitions occur even if the system is in equilibrium. So you have a system whose density large deviation is boring and local and smooth, but if you look at the current large deviation, it has phase transition and is a very rich structure compared to the boring equilibrium one. And indeed, most of my talk will discuss equilibrium problems, and I'll tell you what we know about non-equilibrium problems. I just want to sort of give a comment. There's another mechanism with no microscopic model, which was suggested by the group of Eric Ackermann, which is, I guess, four doors from my office. Okay, so just to show a cartoon of the different transitions and to give you a heuristic picture, which hopefully will guide you through the talk. You could have systems where there's no phase transitions in the large. So this is the large deviation function. This is the current, and I'm plotting it as a function of the current. And as I'll remind you, and you probably know, there's a typical profile of density in the system which realizes each value of the current. And when you have no phase transitions, as you change the value of the current, then this profile changes in a continuous way to support the current that you're interested in. You can have scenarios where you have phase transitions. For example, this is a symmetry breaking phase transition, which I'll describe. In this case, the current, the density profile is smooth until a specific point where the large deviation functional becomes singular. It's a singularity and the second derivative of the large deviation function. So this is sort of illustrated in this figure. And what happens is that the system jumps to another set of solutions. In this case, one of two possible solutions. It breaks the symmetry. And this jumping from this solution to one of these two solutions gives rise to the singularity in the large deviation function. The final scenario that I'll discuss is a first order phase transition. In that case, for small currents, again, the change in the profile is smooth. Actually, it will be flat for what I discuss here. And then there's a region of coexistence where you have two solutions of the current coexistent, essentially the solution sitting here and the solution sitting here, and they coexist in such a way that the average current is given by the current that you're interested in, just like, you know, equilibrium phase separation, exactly the same structure, and once you're beyond another current, then it goes smooth. So this is just an analog of the phase transition that you know from equilibrium systems. So it's a first order. It's linear between, and it's just a first order. Yeah, it's just like coexistence. Okay, and if you bug me, I can discuss more about how the coexistence occurs, because it's a subtle question about how you take limits. Okay, so the outline of, so this is the punchline. So if you don't follow anything, but you follow this, it's okay. Yeah. Okay, much better. The outline of the talks is as follows. I'll first do a quick recap of the formalism just to place everyone on the same footing. I'll discuss the formalism, microscopic fluctuation theory, just really briefly because you all know this. I'll discuss the different ensembles that you can look at the problem and remind you of the additivity principle. And then I'll go on into our work in which I'll describe the transition again for a general model. So I'll just specify the fluctuating hydrodynamics, and from that we actually derive the Landau theory, which describes the transition in different conditions. And I'll give you the gist of the derivation of the Landau theory, And again, I want to stress that our results are not, we don't start from a microscopic model, they're sort of generic. So the formalism again, so I'm again just reminding you of the setup. We have two reservoirs. I'm taking them here because this is what I'll do most of the talk, to be of equal density. And we know that on large length scales, we can characterize the dynamics of the system two linear response quantities. The first is the diffusivity, and the second is the mobility. And their ratio satisfies the fluctuation dissipation relation with the free energy of the system. This is really an equilibrium, so this gives you the probability of observing a given density in the system. So after you do a diffusive rescaling, so I rescale, so there's L here, I rescale L to be the distance to be between 0 and 1, and then I rescale time by the system size square, so it's a diffusive time. Then we can express the dynamics of the system if you do a proper hydrodynamic limit by this continuity equation, where the current is given by fixed plus the noise term with an amplitude controlled by the mobility. And again, this is, I don't have to explain this here, but in the hydrodynamic limit, the noise is Gaussian and weak with an amplitude that scales as 1 over the system size. Okay, so this is the equation that we're going to work with throughout the talk. Our interest is in calculating the large deviation function phi of j, but as you, many of you know, it's more convenient to work many times, and in our case also, to work with a generating function for the current. So we're going to calculate the average over histories of e to the TL lambda, which is like a Lagrange multiplier times j. So this is morally equivalent to changing ensembles in equilibrium stat mech. And we're going to calculate the large deviation function associated with lambda. And this is related to the large deviation function of the current by a Legendre transform. So if I know one, I have the other one for free. So the way to do it is, again, I'll skip many of the details. If you don't know them, I'll give you the gist. So you use a Martin-Seeger-Rose formalism. This is one of the, you end up with a representation of the problem where you're integrating over all the density field, all the histories of the density field, all the histories of a momentum-like field, whose physics I'll discuss a bit in a second. So this is, you want to think about it as a momentum, and then an action with an L in front where L is the system size, an action which has an Hamiltonian structure. So again, rho hat with lambda. Lambda is because we've shifted the variable, but that's a technical point. It's not important. So we have just a Hamiltonian structure with rho hat acting as the momentum, rho as the coordinate, and it's just the analytical mechanics that you study in an undergraduate. Okay, and the only problem is that this is the Hamiltonian, and in general, it's nonlinear and non-fun. Yeah. T and L are both large. And actually, if you bug me later, the way things behave when you have symmetry breaking, for example, depend on how you take the limits. No. No. Because the physics differs a bit. Okay, so this Hamiltonian is just nonlinear and not fun. That's the main problem. Otherwise, everything's solved. So the trick is that L is large, so all we have to do is a saddle point calculation. So we do a saddle point, which really amounts to solving a Hamiltonian problem. So we're solving Hamilton's equations. This is the analog of the equation for the position, and it's given by this equation. So if you look at this, you can identify the momentum field. Its derivative is essentially related to the noise in the system, the most probable realization of the noises in the system just by comparing this to the original fluctuating hydrodynamics equation. And then we have an equation for, if you want, what I'll call sometimes the noise field. Okay, there is a simplification that we can prove that happens for the models that we're considering, which is called the additivity principle. And the additivity principle states that if you look, we're interested in large times. I didn't specify the order at which I take the large time limit, but if I look at large times, then the dominating history is independent of time. So in contrast to Pablo's talk yesterday, there's no oscillating solutions which depend on time, but there's just a solution that's independent of time, and we can prove it for all the transitions that I'll describe here. And then this solve these equations equal to 0, or if you want, in terms of the action, you want what you're essentially doing is looking for the maximal energy of the configuration with the maximal energy of the system. So this is the technical bit, and what we'll be using throughout, I won't spell it out, we'll be solving these equations in a sort of in a useful way. So to summarize what I've told you, so yeah, that's the additivity principle, no time dependence. And you can prove that these are the ones that minimize the action in our case. In sum, we want to calculate this generating function, and to do that, we're solving these equations equal to 0 in our case. And the result gives us the typical density and noise profiles which realize the fluctuation. Okay, so that's the method to doing these calculations. And we're focused on looking for singularities, and specifically when they occur, for which models, and for which boundary conditions, and where. And again, I'm saying this too many times, but there's been examples of these transitions which break the additivity principle. So at the transition, this assumption of time independence breaks down. And again, we can prove the additivity for our case. And there is another work by my neighbor which gives a condition for the applicability of the additivity principle. Okay, never mind. Okay, so what I'm going to do next is show that the transitions can occur of the type that I've described. So specifically, I'm going to derive a Landau theory, and I want to make the discussion clear, so I'll discuss the result in steps. First, I'll describe the symmetry breaking transition, the continuous one, then first order phase transition. For each of these cases, I'll identify a specific microscopic model which has these transitions, and all the derivations will be done in equilibrium. I'll just tell you what we know about out of equilibrium. We can do perturbative results out of equilibrium. And again, I want to stress, to me it's nice that the transitions occur in an equilibrium system. So the Boltzmann distribution is dead boring, but the current distribution is interesting. Oh, yeah. The typical is boring. Okay, depending. If you're an undergraduate, the typical is interesting. Okay, so I'll start with the symmetry breaking phase transitions, and to have a symmetry breaking, we better have a symmetry. So what I'm going to do is look at models which obey a particle-hole symmetry. So for example, about some density which is 1/2. So 1/2 is the point where things are symmetric about. And if we want the dynamics to be symmetric under this particle-hole symmetry, then we have to assume that both the diffusion coefficient satisfies this relation. So it's symmetric about the point of 1/2, which I chose arbitrarily. And again, the mobility satisfies the same condition. That means that odd derivatives of d and sigma at 1/2 are 0. Okay, this is trivial. And again, I'm stressing that I'm considering equilibrium boundary conditions. So if you look at this thing, you think, how can the solutions look like? So I fixed the density on both sides to be 1/2. I'm driving a current through it. Well, a trivial solution is just a flat profile. Okay, this is a solution. The momentum or noise field has a less trivial structure, also not very interesting, just linear. But this is a trivial solution of the problem, which I'm going to denote with a 0. So 0 means the baseline solution. But if I have a transition, then I can imagine, because I have the symmetry in the system, I can imagine that I have some deviation from this flat profile, whose longest wavelength component I parameterize by an amplitude m times sine of the longest wavelength in the system. Okay, so sine pi x. So this is the longest wavelength component of a solution that deviates from the flat solution. And of course, if I have the symmetry in the problem, then the solutions must occur in pairs. So if I have a solution with positive m, then there has to be a solution with minus m. And I'm going to denote these solutions. These are with a 0 for the flat, and these solutions with an amplitude m of the longest wavelength, I'm going to denote with a subscript m. So I have a solution for the density field and the momentum field. Okay, so with this in mind, what we do, and I'm not going to go through the calculation, but the idea is to solve the Hamilton equations in a perturbative way in the parameter m. Okay, so you're doing a perturbation theory and the parameter m. It's slightly more elaborate than that, but it's essentially what I'm telling you. And then I'm going to define a Landau theory by an expansion in m. I wrote it down. It's the difference in the energy of the flat profile and the energy of the solution with an amplitude m. So I haven't specified m. M is a free parameter. I solve the solutions in m. And this is my Landau theory. I'll make it more clear in a second. And then the scaled cumulant generating function, which again is given just by the maximal energy configuration with the maximal energy, is given by so this is tautology, the flat solution minus this Landau free energy. But now, since I've integrated over space, what I have to do to get the minimal, to get the maximal energy is look for a minimum of this Landau free energy. Yes? The current is hiding in this lambda. Lambda is the variable conjugate to the current. Okay, so we're calculating the generating function. So there's a so it's in the boundary conditions on the momentum field. Okay, sorry. I should have specified that. Sorry. Yeah, but it's hiding in the boundary conditions. Yeah, that's just a shift of you can do a shift of variables which translates into a boundary. That's the shift I was talking about before. Okay.
I was wondering whether the transition that you are going to describe to 0 more or less.
Which maximize h, yeah. Yeah. Okay. Okay. Sure. Okay, so again, the idea is that we integrate over space and we're left, this guy, because we've integrated over space, is only a function of m, the amplitude of this deviation, and then the cumulative generating function is given by this expression plus a minimum of this Landau free energy. Okay, and we can calculate the Landau free energy, again, by solving the Hamilton equations in a perturbative way. You actually only have to go in this problem, specific problem, to second order. And what you find out is sort of a textbook Landau free energy for an Ising model. Okay? So the minimum of this guy gives you the best amplitude of the solution depending on the value of lambda. So lambda c is the critical value of the conjugate parameter to the current. We can translate it to the current, which is given by this expression at the square root of a factor, the value of the diffusion constant at the, okay. There's something that I wasn't too clear about. So, but I want to stress, I remind you that I'm looking at a situation where I'm holding the density at 1/2, which is rho bar. So when I write d bar, then it actually means the value of the diffusion constant at 1/2. Okay? And sigma bar is similarly the value of the mobility at 1/2, and sigma bar prime prime is the second derivative of the mobility with respect to the density at 1/2. Okay? So this is our Landau theory. Delta lambda is the analog of T minus Tc. It's the difference between lambda and lambda c. And if you look at this, you realize that there's two conditions to have a transition. The first one is that sigma has a minima at the location that we're expanding. Okay, if sigma doesn't have a minima, then you don't have the usual branching into two other solutions. Okay, and the other condition is that the coefficient of the m to the fourth is positive. Okay, so again, this is a completely general result. You take an equilibrium system, you hold it at the point of the symmetry of the dynamics, and the condition to have a transition is essentially that the mobility has a minima at that point. Okay, that's in essence the result that I'm presenting. So we have to have a minima at sigma. So just to recap, the Landau theory shows a symmetry breaking transition. We need a particle hole symmetry in the boundary conditions and the model, and the mobility has to have a local minima at that point. Yes. Yeah.
Can't you have a negative quartic term but a positive, for example, or
And have a tricritical. We haven't explored that. You might have that. Okay. It could be. Oh, okay. So once we had this, we look for a model which obeys this. And it turns out that I think this might be called the first driven diffusive system to be studied, okay, by the physicist, mathematical physicist. So it's the Katz-Leibovitz-Schwann paper from 1984. And essentially, if you don't know this model, it's essentially a model which where particles hop on the lattice, but with nearest neighbor interactions. Okay, so you can think about it. I won't go into the details, they're not so essential, but the intuitive way to think about it is it's a Ising model where particles hop with a specific smart choice of rates, which mimics the dynamic Kawasaki dynamics of an Ising model with interactions. And specifically for me, the interesting interactions will be repulsive interactions. So in a paper, old paper by Hager and Krug and Schutz from 2001, they outlined how you can actually calculate from the microscopic dynamics the mobility and diffusion coefficient. Actually, the initial trick was already noted. This special choice of this model was already noted by Katz, Leibovitz, and Schwann. It's called a potential condition, if you want to ask me later. And Paul Krapivsky revisited their calculation. He hasn't published it, but he was actually able to get closed expressions for the mobility and diffusion coefficient. Okay, and this is the for the case where the dynamics obey the symmetry that we're interested in. This is the mobility, and what you notice is that as you increase the repulsion between the particles, epsilon signifies the repulsion between the particles. So it's an anti-ferromagnetic Ising model. A dip develops in the mobility. And the way to think about it is that you have anti-ferromagnetic interactions. So if you have a distance, so if you have a particle, empty site, then the system is quite happy energetically. So the fluctuations are reduced compared to a configuration that's far away from that. Okay, and of course, eventually the fluctuations should go away when it's fully occupied or empty, so you expect this double hump when the repulsion is large enough. Okay, so indeed, this model has a local minima for strong enough repulsion, and that means that this model will exhibit the transition that we're discussing. Okay, so summary of the symmetry breaking case, just to recap, we have a system with the local minima of sigma at the symmetric point rho bar. Up to now at equilibrium, we can actually prove perturbatively that if you drive it out of equilibrium a bit in a symmetric way, so at one end it's plus delta rho and the other it's minus delta rho, then the transition survives. Beyond that, we don't know what happens. Okay? So the transition, if I plot the cumulative generating function, it has the second order singularity where the solution again goes from flat to choosing between these two solutions. And when I translate it, do the reverse Legendre transform, it just looks very similar in this case. Yes? Yeah, so we can only give this perturbative statement. Okay, that's all we know. Still, yeah. To leading order in delta rho, there's still a transition. Yeah, exactly the same structure. Okay? Okay, so the next transition I'm going to discuss is the first order phase transition. And again, okay, so symmetry breaking, we have a symmetry. You're looking for first order, you get rid of the symmetry. So we're looking at a model with no particle hole symmetry. Again, in equilibrium, and again, I'm going to hold it at a minima of sigma. I'll discuss what happens when you're not at the minima of sigma. But at equilibrium, and we're sitting at the minima of sigma, you repeat exactly the same procedure that I did before, exactly the same perturbation theory, and you find out that you have this Landau theory. Now you have a quadratic term and a cubic term. And that tells you immediately, if you don't know these Landau theories, I'll show them explicitly in a second. It tells you again that the condition to have the transition is first that you have a minima of the mobility at the point that you're looking. The second condition to have a first order phase transition is that this combination of diffusion coefficients and derivatives of mobilities and diffusion coefficients is non-zero. And then that this guy is positive to have the transition that I'm looking at. And if you wonder how this looks like, then what happens is that for small values of lambda, the solution that's chosen is m equals 0, which is basically the flat solution. Then there's a critical value of lambda where you have a coexistence of two solutions, one with m, which is a flat solution, and another which is a deformed solution, now with a specified sign of m. So this is the coexistence. And then when you cross, this minima dominates and you cross into the solution. So this is, again, a classical first order phase transition. You might be used to it with okay, anyway, it's just a standard first order phase transition. And again, I remind you that the current is related to the derivative of the generating function. So you have a jump in the current. Okay, and the way to resolve it is this flat line, which I'll come back to in a second. Okay, so again, we're looking for a microscopic model which shows this. So we go back to the Katz-Leibovitz-Spohn model, and we have, courtesy of Paul Krapivsky, we have the nice expressions for the mobility. And if you look at a point where you don't have the particle hole symmetry, then you again can identify points where you have a minima, and it doesn't obey all these symmetries. So this is a model that will have the first order phase transition, okay, of this type that we're discussing. Again, just to recap the first order phase transition, we're looking at a system with a local minima of the mobility. At this, we're sitting at that point specifically. We've looked at equilibrium. Again, it survives driving it out of equilibrium to first order in delta rho. And again, when you change ensembles back to the J ensemble, to resolve this, what you do is you do a typical equilibrium constructions where you have a coexistence of one current with the other current. So that means, okay, depends on the order of limits. It means that when you do an ensemble average, either you see one or the other, or you could, if you run it for long enough, it will just jump between the two solutions. Okay, yeah. The red one, well, it's all perturbative, so I don't know what happens. Okay, we're doing a perturbation theory. I expect so, but I don't know so. Okay? Okay, so we have a coexistence, sort of like a classical textbook example, and you could ask what happens when you're not sitting at the minima. So now we're doing the same same theory, but we're not sitting in a minima. We set the density at some other point. So you do the Landau theory again. Now not at the minima, and you find out that the first derivative of sigma enters. So now we're sitting at a point where there's where it's not zero, and you can see that that acts like a magnetic field. Okay, so that kills all the transitions. Okay, just wipes them out completely. Okay. Okay, so summary up to here. I have 3 minutes, but okay, fine, that's fine. Summary up to here, depending on where you are in the shape of sigma, you can have either, so this is sigma has a minima. If you're sitting outside the minima, there's no transition. If you have a symmetry and you're sitting at the minima, you have a symmetry breaking transition. If you're sitting at the minima and don't have a symmetry, then you then you have a first order phase transition, and these correspond to these scenarios. What I want to do is give you some physical intuition to why you have these transitions. Okay? So this is, I remind you, this is our fluctuating hydrodynamics. We have our diffusive part and the noise part. And the diffusive part likes things, and it's hot, and if you're using a large mobility, then it's easier to carry a current, okay, because this is just the current. So what's happening if we sit, let's think about the symmetry breaking transition. If we sit at the minima, if the system is sitting at the minima of sigma and it's flat here, then as I crank up the current, it becomes favorable for the system to use the large values of sigma by climbing up the density. And because I have the symmetry, then I can climb up either to the right or to the left. So to carry a large current, I want to eventually take advantage of the noise term, and the way I'm taking advantage is by breaking the symmetry. Okay, so that allows me to carry a larger current, the fact that I'm using this term instead of this term. It's actually, I haven't derived this, but I assume that most of you know it. If you look at the Lagrangian picture, then you can do, again, the same idea with the Landau theory, expand it to second order. That's enough to see if you have a transition or not. And you find out that you have two terms. The first arises from the numerator, and the second, which arises from the denominator. And you can see explicitly that it's a competition between the mobility term and the diffusion, which gives rise to the transition. So this is sort of a quantification of this heuristic picture that I gave you a second ago. Okay, so the last thing you could ask is the effect of a bulk field. So far I ignore the possibility of a bulk field. You can easily extend the theory to include a bulk field and repeat the same Landau theory as I showed you a second ago. And when you do that, you find almost the same structure, but where the quadratic term is, we have a shift of E. So that essentially means, very similar to Pablo's transition yesterday, that if I crank up E large enough, I don't have to demand that the second derivative of sigma is negative. I can have is positive. The second derivative of sigma can be actually negative. So that means that as long as I'm sitting at the minima, don't know what I wrote here, ignore that. For large enough E, I can have a transition. So that means that if I take the WASEP and I crank up the field large enough, then very similar to the one that breaks the additivity principle, you have a transition also here. Okay, and I think I'm done, just on time. I didn't need to use our relations. So the current large deviation function of boundary-driven diffusive systems can have singularities. We identified models for the different scenarios. In our context, that can be first order or second order. Maybe they're tricritical. We haven't explored it. Transitions are not associated with the breaking of additivity principle. And I think an interesting question is, can you have a boundary-driven system where you have transitions which break the additivity principle? Okay, so a king that travels from one side to the other. Myself, I spent some time thinking about it, and I couldn't make any progress, so any ideas are welcome. So thank you very much for your time.
So that breaking of the additivity principle, what makes it problematic in the so if you look at not just one single traveling profile, but the ensemble of all the shifted traveling profiles for the WASAP, all of these things are still.
But here we have boundaries.
Yeah, no, I get. I'm trying to get to is, for some reason that I don't quite understand, for the asymmetric simple exclusion process, there's no issue. In both cases, you have traveling fronts, but they travel very slowly, and those transitions seem to be the same in both situations. And something must happen somewhere in between, but I don't understand how. In one case, for periodic systems, this seems to go to traveling fronts that break the additivity principle, but for open systems, that doesn't happen.
Well, it's hard for me to imagine something traveling and.
Yeah, of course, but no, so they'd be diffusing, not traveling. Actually, the fronts for the open boundary case.
Yes, maybe that would be cool, but okay.
We can.
Yeah, I'm happy to discuss it. That would be cool to find, but.
Yeah. Okay.
Okay, so maybe a naive question. So in like equilibrium phase transitions, like you change some parameter and then you see something there's transition in some observable. So in this kind of systems, I mean, it looks like you're looking at some distribution and you find a singularity somewhere.
Yes.
But is there like, could I change some control parameter and actually see a transition in something?
So here, not in the typical states, you're not going to see. The typical current is boring, so.
I mean, like, for example, is it conceivable that I could, let's say, change the current in some way? Observe a sudden change in the density profile.
I don't think these are diffusive, so typical states are pretty boring. It just means that if you look at the probability distribution, I mean, if somebody looks for these things experimentally, then it means that if you look at the distribution, there's some enhancement of the fluctuations in the tails.
So you would actually have to look at the full distribution.
Yeah, okay. You would have, people do that. I mean, there are some experiments on heat conduction and people in electronic systems can look at probability distributions of the current. The problem is that diffusive dynamics of the type that we're looking, they're not good for electrons because you have neutrality. So it's, anyway.
Thank you. I have just a stupid one, actually. So you said that when you don't have sigma prime 0, then everything is washed out by the magnetic field. So from your action, it looks like m might be finite even when lambda is 0, which seems not right. So
When you're not sitting at the minima, why is it not right?
have a flat profile at equilibrium, right?
Yeah, but as you increase, let's go back to the Landau theory. If, as you increase lambda, then you'll change m.
It's delta lambda.
Yeah.
I'm being stupid. Am I? No, I think I'm not being that stupid. Anyway, that's...
Okay. Okay, thank you.